Hello everyone. We present our work GeoMAE, Masked Geometric Target Prediction for Self-Supervised Point Cloud Pre-Training. Point clouds are often adopted to offer robust information in autonomous driving perception such as object detection and segmentation. These methods usually demand a large amount of 3D annotations which are hard to acquire. To alleviate this issue, recent works explore learning representations from unlabeled point cloud masked modeling methods. We revisit differences between images and point clouds, and introduce a point cloud representation learning framework based on geometric feature reconstruction. Our method identifies point statistics and surface properties prediction target peculiar to point clouds. These objectives yield a non-trivial self-supervised learning task and mutually facilitate models to better reason fine-grained geometry of point clouds. Now, let's go into the details. Motivated by masked image modeling, some recent work randomly sparsified point clouds are encoded by point cloud feature extractors, followed by a reconstruction module to predict original point clouds. These methods, when applied to point clouds, ignore the fundamental difference of point clouds from images. Points provide scene geometry while images provide brightness. As shown in the picture, this modality disparity hampers direct use of methods developed in the image domain for point cloud domain, and thus calls for novel self-supervised objectives dedicated to point clouds. Inspired by modeling and computational techniques in geometry processing, we introduce a masked autoencoding framework dedicated to point clouds self-supervised learning. Most importantly, we design a series of prediction targets which describe the fine-grained geometric features of point clouds. These geometric feature prediction tasks facilitate models to better reason fine-grained geometry of point clouds. Concretely, our method starts with a point cloud voxelizer. Given an input scene, we first voxelize the sparse point clouds into regular voxel grids. Then, we pass non-empty voxels through VFE layers to obtain per voxel features tokens. Based on evidence from 2D masked modeling methods, we choose a high mask ratio when removing tokens. After random masking, only visible voxel tokens are fed into an encoder. Due to the sparse and long-range nature of the input scene, we choose a sparse transformer proposed in SST as our encoder. Then, the output token of the encoder and the learnable mask token are fed into two split decoders. One is to decode the point statistics including occupancy prediction and centroid prediction. The other one is to decode the surface properties including normal prediction and curvature prediction. Different from 2D images and 3D indoor point clouds, outdoor point clouds are sparse and occluded. To deal with non-uniform points, we opt to predict the centroid and occupancy of each voxel, which belong to the point statistics. To incorporate multi-scale information, we aim to predict these statistics in different scales by building a voxel pyramid. For each masked voxel token, points inside the voxel grid are break into three sub-pyramid voxel levels: the top level, the middle level, and the bottom level. Voxels and pyramid levels have different voxel sizes. And the voxel size of the top level is the original voxel size of the masked voxel token. For each non-empty voxel grids in the three levels, the centroid prediction target is calculated by averaging the coordinates of points inside the voxel grid. The occupancy prediction target is to judge whether a grid is empty or not. If there are at least one point in the grid, the occupancy prediction target is 1. Otherwise is 0. Although point statistics provide a rough estimation of shapes, they cannot describe the fine-grained geometric information that are usually critical to recognition tasks. Therefore, in addition to point statistics prediction, we further predict surface properties for the masked token. Inspired by surface feature estimation, we apply local least square fitting to handle noisy LiDAR point clouds. By using centroids of the neighbor voxel grids to represent the local point clouds, we compute a covariance matrix of this point cluster. After the eigendecomposition of the symmetric matrix, we obtain values λ1, λ2, and λ3, and their corresponding eigenvector n1, n2, and n3. The normal prediction target for each voxel is the corresponding eigenvector of the least eigenvalue. Moreover, we adopt the normalized eigenvalues as the pseudo-curvature prediction target. The point statistics and surface properties describe the fine-grained geometric features of the point clouds. These geometric feature prediction tasks jointly drive models to recognize different shapes and areas of scenes. To demonstrate the effectiveness of GeoMAE, we evaluate our method on several downstream tasks, including 3D object detection, LiDAR semantic segmentation, BEV map segmentation, and 3D multi-object tracking. For 3D object detection, we compare our GeoMAE with several typical 3D self-supervised learning methods including point contrast, STRL, BYOL, and SWAV. Our GeoMAE outperforms previous methods by a significant margin on both Waymo Open Dataset and Nussein's data. We also evaluate GeoMAE with different detection head to demonstrate the generalization of our method. We further experiment our method in the LiDAR semantic segmentation and BEV map segmentation task on the Nussein's dataset. For LiDAR semantic segmentation, we adopt Cylinder 3D as the baseline architecture. For BEV map segmentation, we choose Centerpoint and BEV Fusion as the baseline model. Our method surpasses the baseline models on both segmentation tasks. We also conduct experiments in a 3D multi-object tracking task on the Nussein's dataset by performing tracking by detection algorithms proposed by Centerpoint and SimpleTrack. From this table, we can see that our GeoMAE outperforms the baseline by 1.7 iota for Centerpoint and 1.1 iota SimpleTrack. These observations are consistent with those in 3D object detection. That's all, thanks.